This is part 2 of week 5 lecture, and we're going to talk about the water requirements and how we might take account for those to help us understand the environmental impact. First of all, let's just talk about water requirements for human health and agriculture. So just for human health, just to survive, it takes about 3 liters per person per day. That's a very small amount. For hygiene and sanitation, it's 50 liters on top of that. And so when you're talking about making water available to, say, rural, undeveloped areas, it should be in this range of about 50 liters per person per day so that they have enough water to drink and cook and perform their normal hygiene processes and keep everything clean. So just 3 liters keeps them alive, but 50 liters can keep them healthy. So in year 2000, about 55 countries were below this level of 50 liters per day. And then there's a wide area of the world now, estimated to be about 2 billion people that don't have adequate clean water for their personal use. So that's just personal use. The biggest user of water on the planet is agriculture. And this is because we use agriculture in all sectors of all types of economies to provide the food for our livelihood. And as the population is increasing, the demand for agriculture is increasing. So we're going to come back to this a little bit later, but water in the life cycle analysis, but water used for crops production is not constant either. We talk about the water efficiency, which is the kilograms of crop produced per meter cubed of water, or the grams of crop produced per kilogram of water. And this depends on many variables: humidity, crop type, wind. So that means it's going to change all around the world. Different crop types require different amounts of water depending on where they are, what the local weather is, and what type of crop it is. So when we talk about the amount of water required, one of the articles in the reading shows the distribution of water in this sort of stacked these stacked boxes. The fresh water is only 3% of the total water. This other saline water we really can't use for human consumption. Of that, about a third of that, or 1% of the total, is groundwater, and the rest are ice caps and glaciers. And then when you look at just the surface water, which is only 0.3% of the fresh water, it's lakes and rivers and some swamps. So again, this is the category of water that's directly usable from surface water, and then we can get at groundwater through pumping. And one way we'd look at this is by, in the United States, where does this water go? So this is characteristic of a developed country that has a lot of thermoelectric generation, whereas the biggest two users are irrigation and thermoelectric. That is water running through power plants, coal and natural gas, nuclear power plants. They need water for cooling in order to work. So these are the two biggest users, and they just dwarf domestic water supply. And that domestic water supply is water going to households for people to drink, shower, wash, water their lawn, clean their car, all sorts of purposes. It's not just survival water supply in the United States. So even then, the irrigation and thermoelectric together are many times greater than this domestic. So whatever we do in domestic water consumption is just really small compared to what's going to happen in irrigation. We're going to see this later in terms of the amount of water that's embedded in a product. It's largely because of this irrigation and water used for maintaining livestock. So that's sort of an idea about the water demand, but the water water is a particular type of resource. It's a renewable resource. There's 3 basic types of renewable resources. One is recycled. This good example is aluminum. You use it, then you recycle it and use it again. And there's some areas in the country where they recycle water. That is, they drink it, then excrete it, and other uses, shower, whatever, goes into the sewer. There's processes to clean it up, comes back into the domestic water supply. So San Diego, for example, uses a lot of recycled water. In parts of Texas, this is the only way that they're going to get any water, so they have these recycling water supplies. Water that we're going to be talking about mainly is physically renewable. That is, there's some sort of, it's driven by solar energy coming into the planet, drives the hydrologic cycle, and then these physical processes create a flow of water through, we capture that as a resource as it flows through our particular landscape. Then there's biological renewable. This would be a good example. Would be trees. You grow trees, you cut them down, they grow again. You cut them down, you grow again. This is what you might call a biological renewable. So we're going to focus on this physical renewable aspect of water, and this is driven by the hydrologic cycle. And the hydrologic cycle is really a stock and flow diagram of where the water is and where it and how it goes between different components. And so again, we have the largest reservoir of water is the ocean. It's not really that useful to us in terms of water supply for human use. The stocks that are useful to us are lake and reservoirs. This is only labeled with lake, but a lot of water is stored in reservoirs, and the groundwater. So those are the sort of stocks, if you would, that are important to us, and those are supplied through rainwater or snow coming in the mountains and melting off, coming in the streams, feeding in the lake. Some of that water that's on the landscape goes down and replenishes the groundwater. So we have rain coming into streams and rivers supplying lakes, and we have recharge of the groundwater. To get at lakes, it's just surface water use. To get at the groundwater, we need to use wells and pump the water out of the ground for our human use. So in this landscape, we have all the water uses, and then we have these sorts of replenishment factors, just rain or snow, and then that's either goes into lakes and rivers or into the groundwater. So that would be the total water available to us as a society, is how much of this is being rain into the rivers or recharging the groundwater. The absolute max that we could get at in this particular landscape. So let's talk about water shortage. And water shortage, I'm going to go through a couple figures. Again, this is in the reading, a couple figures that show how much water is used, just how we might think about water use, and then how much water is coming in from this rain and groundwater recharge, and then lump those into an overall figure that shows water shortage by country. So here's groundwater withdrawal by states, and you can see some is millions of gallons of water per day. You can see some states that are high agriculture states have a lot of groundwater withdrawal. Texas, California, Nebraska. Surface water use. Different still, you get the high agriculture states of California and Texas using that, but then you start seeing states like Oregon and Idaho having a lot of surface water withdrawals because we have more rain and snow, so we get more water just coming that way. And then all through the east, you have the much more water sufficient states where the amount of water coming in is coming in from rain every year and it's just reused. So if we combine that sort of information with the availability of fresh water on a global, so on a country level, here's the average river flows and groundwater recharge. And you see countries that are blue have lots of recharge. You have countries that are brown and yellow have very little renewable water available. And you put those two figures together, that is how much water they need compared to how much total is available, and you get this freshwater stress table. And in 1995, you see states, you see countries that had maybe this light blue is between 10 and 20%, so the United States used between 10 and 20% of the water that was available to it through rain and groundwater recharge was used. And then you fast forward 30 years, you see that the United States is using between 20 and 40%. And this is due to increased population, increased demand for water. It's not due to climate change variability. This is just based on water projections. And some of these areas, see, we're already water stressed, and then you move to 2025, and it's severe water stress. Now just remember, if I draw this little circle over here, includes China and Indonesia, that's half of the world's population lives right in that little circle. So half of the world population, even in industrial countries like China and in this whole region, are going to be water stressed. Now the importance of water stress is, of course, environmental. The more water humans take off the landscape, the less there is for natural processes, river flow, forest growth, all those sorts of things. And the other part is very geopolitical about food stress. When you have water stress, and remember, over half, the biggest water user in industrialized countries was agriculture, and by far the biggest use in non-industrialized countries is agriculture. So agriculture produces food. There's going to be food stress and food insecurity associated with this water stress. Okay, another final point about water is that one of the things we'd want to watch would be water pollution. And this is important because remember, we're talking about in environmental accounting, what are the categories? I give this quick example in part 1 about here's the types of water and the quality of water. Well, water pollution is really when you take maybe a source that otherwise available and you make it unusable by having pollution. So pollution is considered a loss of usable water. And right now the amount that we're losing to pollution is enormous. Some countries are in really tough shape. So for example, South Africa, the groundwater was polluted by industrial processes, including mining, and now the surface water is being polluted by agriculture. So they really don't have any way to store water underground in groundwater or to store it in reservoirs because of the pollution. And just contrast that to California, where we can pump water into groundwater aquifers to store it if there was excess water. This impact on water pollution is not only sometimes not acutely felt, but over a chronic period of time. So it's estimated that 40% of the people in China have some sort of liver disorder associated with chronic exposure to low levels of toxins in the water. And just to show how serious this might become, in the USA they've linked Parkinson's degree, looking at counties all across the country. You can follow this link to see a map of that, county by county. And many of these rural agricultural counties have high levels of Parkinson's, and they think it's from low levels of transport, or they hypothesize low levels of transport of toxins from agriculture into the water supply. And in an even stranger case, in Vermont, the appearance of ALS was determined by using GIS mapping. There was a bunch of people that were getting ALS, but they weren't in any one place. But when they tracked it down, they found all these people lived on little lakes or ponds that had cyanobacterial blooms and had put toxins into the water. So here we have the impact of pollution being very subtle and over long periods of time. Hard to track. You really have to find out what all those water sources are, what the category of pollution or cleanliness is in the water, and that's really the forte of an environmental accounting approach.